Hi, everybody, and welcome to our very last video for linear algebra. My cat is sitting close by purring. I don't know if you'll be able to hear him or not, but if you hear a low kind of rumbly sound, that's what that is. So he's here to comfort you through your last linear algebra video. So sad. So we're going to start this video with two definitions and a theorem, and then we'll work through a couple of examples. And that's going to be it. So let's start out with our definition for orthogonally diagonalizable, which is what this video is about. So if a matrix A can be diagonalized using P, where P is an orthogonal matrix, of eigenvectors, then we say that A is orthogonally diagonalizable. All right, there we go. In other words, in order just to be diagonalizable, right, that means that you have to find an invertible matrix P so that A is equal to P D P inverse, where D is a diagonal matrix. Right, so we had A is P D P inverse. So this is what we used in order to diagonalize a matrix. So here, we're going to be orthogonally diagonalizable if P is an orthogonal matrix. So remember that in order to be an orthogonal matrix, you're really kind of like an orthonormal situation where the columns are, if you think of those as column vectors, those are going to be orthogonal to each other. So their inner product will be 0 and their norm is 1. So when we have an orthogonally diagonalizable matrix, or when A is orthogonally diagonalizable, not only does P have to be invertible, but it has to be orthogonal as well. So from this, we get theorem 29. And theorem 29 is the following are equivalent kind of theorem, which means if you know one of the items on this list, you can assume the other two items. So A is a real n by n matrix. N by n matrix. Then the following are equivalent. One, A is symmetric. Two, A has an orthonormal set of eigenvectors. And three, A is orthogonally diagonalizable. All right, so in our previous video, we did look at symmetric and skew-symmetric matrices, and we had a theorem that said if a matrix is symmetric, then its eigenvalues are purely real and its eigenvectors are orthogonal. So what this is saying is 1 and 2 are basically saying that theorem, but just going a step a little further. So they're saying if you have your symmetric matrix, not only do you get an orthogonal set of vectors, you get an orthonormal set of vectors because you can just normalize those orthogonal vectors. And then since you have that orthonormal set of eigenvectors, we can use those to create our matrix P so that we have an orthogonally diagonalizable matrix. So theorem 29 is basically saying if we're going to be orthogonally diagonalizable, we're going to have to be a symmetric matrix. So if you're asked to give an example of an orthogonally diagonalizable matrix, all you need to do is give me an example of a symmetric matrix, right? So we have one more definition, and then we'll work through an example. So we're going to call this definition 27. And here's what it says. It says we're going to let A be an n by n matrix. Then the principal axes of A that's what we're defining here, is a set of orthonormal eigenvectors of A. All right. So in other words, think about when you go to draw the standard set of axes for R2, right? So you have your x-axis and your y-axis. And if I think about our standard basis for that space, our first vector would be 1, 0, and then we would have 0, 1. So these are two orthogonal vectors, and they are normal vectors because they each have a length of 1. So this is a very nice set of axes for us to use in R2, and we can generalize that concept not only to Rn, but to any n by n matrix. And that's how we're going to create our principal axes of A. Okay, so the principal axes are orthogonal eigenvectors, and they are normal eigenvectors. So that's kind of in the background where this principal axes terminology came from. It came from our principal set of axes that we use to graph in R2. So let's do an example where we find the principal axes of a matrix. So I'm going to erase the board so I can write the problem down, and then we will work through it together. Alrighty, so, oh, excuse me. Example 44 says this matrix A has eigenvalues of -3, 2, and 0. And they'd like us to find the principal axes of A. So remember, the principal axes mean they want us to find an orthonormal collection of eigenvectors for this matrix. So in order to be able to do that, we have to check, is this matrix symmetric? Because of the following our equivalent theorem that we looked at. So if we check out A, it is indeed symmetric. Again, if we reflect over the main diagonal, or if we take its transpose, we get the same thing, right? 1 and 1, 2 and 2, -1 and -1. So we are a nice symmetric matrix. So to start out with, before we find our orthonormal eigenvectors, let's just find the eigenvectors. So we have the 3 eigenvalues, so we can find the eigenvectors. Remember, we can do that by substituting into xi minus a. We substitute in each of the eigenvectors one at a time, and then row reduce to get our eigenvectors. So let's do one of those together, and then we can pause the video and we'll each work through the other eigenvectors independently. So let's use lambda 1 of -3. So I'm going to start out with xi minus a. And I'm just going to use lambda here because we have our lambdas defined over here. So we're going to have lambda minus 0, which is lambda, -1, -2, -1, lambda plus 1, 1, -2, 1, and lambda. So this is our lambda I minus a, and this is where we're going to be substituting in each of these eigenvalues one at a time. So let's throw in -3. So this is going to give me negative, well, let me announce that here in my work here. So lambda equals -3. So I know which one I'm doing this for. I found the squeaking marker again, I apologize. So we're gonna get -3, -1, -2, -1, -2, 1, -2, 1, and -3. And I just got this -2 because I did -3 plus 1, and that gave me the -2. So in order to find the eigenvector, remember the eigenvector is the solution to this homogeneous system. So to find the solution to this homogeneous system, we're just going to row reduce. So I went ahead and threw that into my calculator earlier. And from that, I got the following matrix. I got 1, 0, 1, 0, 1, -1, 0, 0, 0. So when we use our reduced or echelon form of our matrix, this is what we end up getting. And remember, there's an invisible column of zeros here. So because we don't have a pivot position for z, that means z is going to be our parameter of t. Y is, if I move this over, going to be t. And then when I move this over, x is going to be -t. So if I think about the vector that this is going to end up giving us, we get t times -1, 1, 1, which means for this eigenvalue of -3, our first eigenvector is -1, 1, 1. All right, so I'm going to ask that you pause the video here and repeat this process for your eigenvalues of 2 and 0 to make sure that you can find their corresponding eigenvectors. I'm going to do the same, and then we can compare. So I'll be back in a moment, but make sure you pause and work through it first. Okay, so I've gone ahead and found our other two eigenvectors. So when I had lambda 2 equaling to 2, I substituted that in. I row reduced, and I got an eigenvector of 101 Dalmatians, so 101. And then for my eigenvalue of 3 equal to 0, I substituted 0 in for lambda up here, row reduced to row reduced or echelon form. And then I got an eigenvector of -1, -2, and 1. So previously, we had a theorem that said this would be an orthogonal collection of eigenvectors. So I wrote them up here for easy reference for us to look at. So let's check to make sure that they are in fact orthogonal to kind of confirm that that theorem worked. So we would do the dot product between these two. So we're going to get 1 plus -1, sorry, plus 0 plus 1 is 0. That's good. Between these two, we're going to end up getting 1 minus 2. So we get a -1 plus 1 is 1. That works. And then between these two, we get -1 plus 0 plus 1 is 0. So these are all orthogonal eigenvectors, which is wonderful. But we're not done yet. No, because we need to find the principal axes of A. And not only are the principal axes of A orthogonal, they are also orthonormal, which means we just have to normalize these three vectors. So I'm going to erase all my work here. That's also why I wrote those up top for some easy reference. And let's just normalize them. So remember, in order to normalize a vector, you have to find its norm, which is just the square root of the inner product with itself. And then we'll divide by that value. So let's find the norm of x1. So that's going to be the square root of, now when we find the dot product of a vector with itself, you just square each of the coordinates. So we're going to get 1 plus 1 plus 1. So we get the square root of 3. So to normalize x1, we just divide everything by root 3. So we're going to get -1 over root 3, 1 over root 3, and 1 over root 3. But of course, we don't want to leave it in that format. We want to make sure that we can simplify our radicals. So we're going to rationalize the denominators, and that will give us a -root 3 over 3, root 3 over 3, and root 3 over 3. Cool. So we can zip through normalizing the other two vectors as well. So you know the game by this point. I'm going to pause the video. You're going to pause the video. You're going to find the norm for each of these two vectors, divide by it, and rationalize denominators when necessary. Once you're done, unpause the video, and you'll see my work on the board. Here we go. So how did we do? Did we find our orthonormal eigenvectors? Let's see. So my norm for my second vector was root 2. So I just divided by root 2 or multiplied by root 2 over 2 and ended up with root 2 over 2, 0, root 2 over 2. And then for my third eigenvector, it had a norm of 6. So I divided by, a norm of root 6. So I divided everything by root 6. Here you can see me rationalizing the denominator here to get some simplified action in our second term. So these three vectors are a collection of orthonormal vectors. Their norm are all 1, and they are each orthogonal to each other. You can check that on your own if you wish. And so these are going to form our principal axes for our matrix A. Now, in this particular example, we had 3 distinct eigenvectors, which means we ended up with 3 distinct, we had 3 distinct eigenvalues, which gave us 3 distinct eigenvectors. So we knew that this process was going to give us our matrix P as we wished. However, remember that sometimes you get a double or a triple or quadruple or n-tuple multiplicity for an eigenvalue. So you can get anywhere from n or below eigenvectors associated to that eigenvalue. So when this happens, when you have an eigenvalue with multiple multiplicity, so something bigger than 1, you can get multiple sets of orthonormal vectors for your, or orthogonal vectors for your matrix. So let's write that formally in a note, and then we'll do an example where it's possible to get more than one collection of orthogonal eigenvectors, but we're just going to find one, but we'll see why we might be able to get more than one. Alrighty, so let's formally write up that note that we were just discussing. So this is note 11, and it says, if a real symmetric matrix has eigenvalues with multiplicity greater than 1, it's possible to find multiple sets of orthonormal vectors Alrighty, so I have example 45 over here on the side. This is going to be our very last example for the course. And we're going to find an orthogonal matrix U that will diagonalize this matrix A. Now, just a reminder, in order to find an orthogonal matrix, not only do the columns need to be orthogonal to each other, but they also have to be orthonormal vectors. So they have to have a norm of 1 as well. So we're going to start this problem by finding the eigenvalues for A and then finding the eigenvectors for A. So since this is our last example, let's treat it as a review problem. So pause the video and find the eigenvalues of A and their corresponding eigenvectors. You should get an eigenvalue that has a greater than 1 multiplicity. So pause the video and work through that here. And when you're all done, you can unpause and my work will be on the board and we can check our solutions. Alrighty, so let's see how we did finding our eigenvalues and our eigenvectors. So to start out with, I took xi minus a, threw that up here, and then I found its determinant, set it equal to 0. So when I worked through that, I expanded along the first row. I was very grateful for those 2 zeros. So I got x plus 1 times x minus 2 squared minus 9. So that's where this came from. Now, I was also very grateful because this is a difference of perfect squares. It's x minus 2 being squared, and then we have 3 being squared. So that would factor into x minus 2 minus 3 and x minus 2 plus 3. So when I simplified and combined my common factors, I got x plus 1 being squared times x minus 5. So notice here we have one of our factored components being squared. So that means -1 had a multiplicity of 2. It happened more than once. And 5 had a multiplicity of 1. So when this happens, because I'm listing -1 as my first eigenvalue, I actually have to list it twice because it had a multiplicity of 2. And then x3 is my last one. We ended up with 5. So then I threw those into the matrix and row reduced in order to find my eigenvectors. So using -1, when I put that in, I got this matrix, which row reduced to this one over here. And you'll notice that we only have one pivot position. This is actually good news because our multiplicity was 2. So we want 2 pivot positions. So we end up with 2 different eigenvectors. So I used t for my parameter for z, and I used s for my parameter for x because x did not have a pivot position, neither did z. And y can be defined in terms of z, so y is going to be t. So this gave us 2 eigenvectors, one corresponding to the s. So here I have one s, none, and none. That's how I got 1, 0, 0. And then for this one corresponding to the t. So I have no t, 1, 1. So that's how I got 0, 1, 1. Then for my other eigenvalue of 5, I threw that into this matrix and row reduced here. One eigenvalue, so unsurprisingly, one parameter. So I end up with one eigenvector. So the eigenvector I got here was 0, -1, and 1. All right, so I'm going to step out of the way in case you need to pause and review any of this to kind of check your work. But we are not done yet. We have to find an orthogonal matrix U that's going to diagonalize A. So to find that orthogonal matrix, remember the matrix that we can use to diagonalize A is just its columns corresponding to those eigenvalues. So, or the columns are the eigenvectors, sorry. So we can use these 3 eigenvectors to form those columns, except we wish for U to be orthogonal, which means not only are those columns orthogonal, but they are orthonormal. They have a norm of 1. So go ahead, pause the video, and normalize each of these 3 vectors. I'm going to do the same. And then once you're finished, you can unpause and check, see if we get the same normal vectors. And then, yeah, and then we'll find our matrix. All right, so let's see how we did. Very fortunate for us. The first eigenvector that we had was 1, 0, 0, and its norm was 1. So we didn't have to mess with that one at all. We got 1, 0, 0. For the second one, however, its norm was √2. So we did have to divide through by √2 and rationalize our denominator to give us 0, √2 over 2, √2 over 2. And then similarly here with x3, it had a norm of √2. So we ended up with 0, -√2 over 2, √2 over 2. So throwing these in as the columns of U, we would get 1, 0, 0, 0, √2 over 2, √2 over 2, and 0, -√2 over 2, √2 over 2. So there we go. That is our matrix U. It's orthonormal. Well, the vectors, the column vectors are orthonormal, so it's an orthogonal matrix, and it's going to diagonalize A. So I did want to take one moment after this example. Let me move out of the way again, in case you wanted to pause here and check your work. But I did want to kind of reference the note we did before this example and show you how you could get actually a different set of orthogonal eigenvectors. We're not going to do the full example, but just kind of start it off so you can see. So when we found these two eigenvectors for x1 and x2, I'm just going to erase this so we can get some space here. It was because we had our matrix that row reduced to 0, 1, -1, right? And we were able to set up our vector x, y, z was equal to t, t, and s. Now, typically, when we have been finding our eigenvectors, we separate out s and t, and then what we're really doing is we're setting one of those values equal to 1 and the other one equal to 0. But you don't have to do that if you want to find eigenvectors. For instance, if I were to have s equal to 1 and t equal to 1, then I could get an eigenvector 1, 1, 1. So this is another eigenvector for our matrix A. So this would also work. The problem is now if I had, instead of 1, 0, 0, for instance, if I had 1, 1, 1 as my first eigenvector, well, now I've got to find another eigenvector that's orthogonal to this one. So the way we would set that up is I would take that eigenvector. Now this is essentially, right, the crux of what our space is looking like. So I'm going to dot that with STT. And I need that dot product to be 0 because this new one that I find, this new STT, has to be orthogonal to this one that we picked. So when I do this, I end up with the equation that s plus 2t has to be 0. In other words, s has to be -2t. So if I wanted a second eigenvector that's going to be orthogonal to this one, I could pick, for example, t equaling 1. And if t is 1, then s would have to equal -2. So I would then have -2, 1, 1. So we could have done this whole problem with, we still would have had that same red eigenvector with the eigenvalue of 5, because that only had multiplicity 1. But because our eigenvalue of 1 had, -1 had multiplicity of 2, we now have 2 parameters to play around with, so we can get multiple different combinations of orthogonal eigenvectors. So instead of using 1, 0, 0 and 0, 1, 1, we could have just as easily used 1, 1, 1 and -2, 1, 1. And then we would have used these coupled with that third one that we had found. So that's how, if you have multiple eigenvalues, you can end up with multiple sets of orthogonal eigenvectors, which then we would normalize these. And I just personally, I prefer setting, one of these equal to 0 and the others equal to 1, so that I get things like this one here happening. But it is important when you find your eigenvectors to make sure that they are orthogonal, in fact, so that you haven't made any computational errors anywhere. All right, folks, so that's going to be it for this video, and it's going to be it for this this course. So I hope you found this series of videos helpful, and yeah, so I hope you have a wonderful day, and a wonderful day after that, and the next day, and the next day, and yeah, so there we go, that's it. I can't say it until next time. So this is going to be an awkward goodbye. So farewell, my friends, and if you're in my class, I will see you in class. Bye.